Alright, so hello. In this video, we'll talk about resolution of a vector in rectangular coordinate system. Now, there's a reason we work in a rectangular system, and by that I mean that the vectors about which we resolve a given vector, say v, we resolve it about two vectors a and b in such a manner that they are 90 degrees. The reason behind doing this is because it's very convenient. Later on, we'd find out that this condition of introducing the vectors, the decomposition vectors, the resolution vectors a and b at 90 degrees to each other really plays out eventually. So keeping that in at the back of your mind, we can work out certain other things at this moment quite easily. So if you take the hint from this word here, rectangular system, well, it's no coincidence that a rectangular system has similarities with the rectilinear coordinate system of x and y oriented at 90 degrees. So like with this situation here, what we're trying to do is we're trying to take a vector v, let this be the v vector that we're concerned with now. I'm not ensuring that this v vector is parallel to this and has the same magnitude as well. That aside, we want a vector v, and only that, we actually want two decompositions. So first decomposition would be along the x direction. So this is, say, v sub x vector, and let this vector here be the second decomposition, pointing in the y direction. So that's v sub y vector. Notice that they are at 90 degrees as what we intended here. So with this in mind, and with this basically the same diagram here, but with a proper framework and proper nomenclature, we can go ahead and write our addition rule. V vector turns out to be v sub x vector plus v sub y vector. So that is your resolution. That's how you express the resolution, that's how you express the decomposition, and basically it's reiterating your resultant rule or the rule of addition. Now, that said, let's look at what happens to a vector when we express it in terms of its magnitude and direction, right? So with any vector, in fact, say a vector A, we know that A is the same as writing a vector is the same as writing A magnitude multiplied by a's direction. So if you have a vector a vector here, this is the same as writing a vector in the direction of a, which is given by this term here. So this line here represents the direction of a. This is a cap, and a cap is basically a unit vector. So if this is a cap, then this is 1 unit in length. This is a cap and points in the same direction as a, so it's parallel to this line there. And we must multiply this by a scalar, and the modulus of a is a scalar. And if that's a scalar, we're essentially changing the length of our unit vector in that sense. We're modifying it. So we modify it so that it makes a total of modulus of a length. That means length here. Let me redraw that again. I'm certainly bad with lines. Right, so this works out. So this is the same length r as the length we started with, which was the length of a vector. So basically it's stating that a vector can be separated into its magnitude and can be separated in its direction, the two components of every vector out there. All right, so let's keep that in mind, and also the fact that the unit vector is a special, this is a unit vector, is a special vector with a magnitude of 1 and only a direction. So if you want to further sort of decompose or express the unit vector in this form, that would be the vector's magnitude multiplied by unit vector's direction. And since this term here is the magnitude of the unit vector, which is 1, which gives us 1, so the 1 times a vector is still a vector. So it really doesn't give us anything more. It's basically a tautology that a unit vector is the same as a unit vector. It's really no information. But so, I mean, that is how it plays out. That's the property of unit vector. that the magnitude is 1, and the only information it really has is specified by its direction and not its magnitude. The magnitude is always 1, so that is something that every unit vector holds. So you could have any other unit vector. So if a unit vector was in this direction and had a length in terms of its magnitude, you could have any other vector, say this vector. You could call that b cap. Now again, if this is b cap, this length must be the same as any other unit vector, and we must have that as 1 unit, but it could point in some other direction. So essentially every other unit vector is separated and is distinguished by just their directions. The magnitudes are all constants. Now, even though we write these as a cap or a hat with this symbol as a cap or a hat, they're essentially vectors which cannot be further expressed in this form because that gives us a tautology. So that also in mind, what we can do is we can do this kind of expression, expressing this vector A. We can do this with our vectors v sub x and v sub y. So let's have a look at that. So v sub x is the vector, and we can write this as the magnitude of v sub x multiplied by the direction of v sub x. So this is a unit vector pointing in the x direction, and we can do the same thing with y. So let me leave some space there and let me write this again. So this would be v sub y, its magnitude, multiplied by the direction of v sub y, right? So this is how it plays out. All right. Now, certain things can be substituted just by looking at the diagram and invoking a different parameter. So the different parameter that we want to use now is our angle theta. If you remember from coordinate geometry, we use this angle theta quite extensively because it helps us define slopes of lines, the angles that they make with the x-axis, and basically the gradient of lines. So with this angle as theta, this length here as modulus of v, and this triangle here has 90 degrees, well, we can write that this length here, we can get rid of this for the moment, this length here would be the modulus of vx, and by rules of trigonometry, this should be the same as, well, the hypotenuse times cosine of theta. Similarly, this length here must be the same as modulus of v sub y, and which should be the same as modulus of v times sine of theta. So we can use this this information here and this one there in our expressions for vx vectors. So this turns out to be, let me change the color again. How about a pink? Yeah, let's use a pink. We haven't used pink in a long time. So v sub x would be, this would be the vector v times cosine of theta times the direction of v sub x. And similarly with this would be v vectors modulus times the sine of theta times v sub y's direction. So this is how this could be written as, and let us have our expression of v here. Let us write it at some corner so that we don't forget it. So we have expressed v sub x and v sub y like so. Now it becomes more convenient to express v sub x and v sub y in a different notation, because if you take any other vector, say a vector in this direction, this b are different vectors, say vector t, then even t sub x would point in the x direction, and t sub y would point in the y direction. So that is to say, v sub x and v sub y are not really properties of the vector, but they're properties of the rectangular coordinate system that we choose to specify them in. So we can really get rid of the v component of these terms here and just write them as general terms. So they could be something like something that only take into account the directions of x and y. And physicists do that by calling v sub x a unit vector as I cap or I hat, and calling v sub y unit vector as j cap. So with that said, we have the following. V vector turns out to be the modulus of V vector, cosine of theta, times I cap. I cap is a unit vector in the x direction. J cap is the unit vector in the y direction. And we have the second term to be that associated with y. So that would be V modulus times sine of theta times the j cap. So this ultimately becomes our rectilinear resolution of the vector v. So we can do this with any other vector. All we need to take into account is the length of the vector, the length, that means the modulus, which is used here, the angle that we specify it with, that is used here, and I and j are the same as always. They would be the one pointing in x, the one pointing in y. So that's how you resolve the vector in a rectangular coordinate system, and this is what you mean by using a coordinate system and expressing a vector there. So I hope this video made sense. I hope it helps you to understand the importance of a rectilinear coordinate system and the fact that we discussed coordinate geometry before discussing vectors, and there was a reason to that. I hope you understand the reason as well. And basically, I hope all this made sense. So all the best and have fun.